Hello everyone and welcome to this quick concept session brought to you by Physics Forum, where your success is our mission. Today we will dive into a fundamental topic in inorganic chemistry that's crucial for both NEET and JEE, that is periodic trends, and specifically the periodic trends of atomic size. Understanding how atomic size varies across periods and down the group not only helps in answering the theory-based questions but also builds your foundation for related concepts like ionization energy, electronegativity, and reactivity. So before we understand the trend, let's first know what atomic size or atomic radius actually means. Atomic size is the distance between the nucleus and the outermost shell of an atom, basically how far the last electron is from the center. It tells us how big or small an atom is. Now, since we cannot directly measure the boundaries of an atom because electrons move in clouds, Heisenberg's uncertainty principle, so we use indirect methods. The most common way of measuring the distance between the two nuclei of two bonded atoms and taking the half of that distance. For example, if we have a hydrogen molecule H2, we find the distance between the two nuclei, that's called the bond length, and half of it gives the atomic radius. So remember, atomic radius is a calculated value and not directly observed. So in this diagram you can see the nucleus that is made of protons and neutrons, and electrons are revolving around in the shells. The atomic radius is measured from the nucleus up to the outermost electron shell, from here to here. That is the atomic size. But atomic size, as we have already talked about, it cannot be measured directly because atoms are incredibly tiny, and instead we rely on experimental techniques that gives us an idea of how large an atom is. Two widely used methods are spectroscopy and X-ray diffraction. So as we move across a period in the periodic table, the atomic size decreases. That is the trend. Let's look at the reasons why it happens. First is the number of electron shell remains constant across a period. We know that, but the nuclear charge increases because more protons are added to the nucleus from left to right. So this gives a stronger positive pull. The electrons are pulled closer to the nucleus, so increasing the attraction between them. As a result, the atoms becomes smaller and smaller in size as we go from left to right across a period. Suppose let's take an example of sodium. Sodium's atomic number is 11. So sodium has 11 electrons, and its electronic configuration will be 1s2, 2s2, 2p6, 6 plus 2 plus 2, 10, and 3s1. So sodium is at the left, group 1, and chlorine, if we take the example of chlorine, in the same period 3, chlorine will be at the rightmost corner, and its electronic configuration, electrons are 17 because atomic number is 17, and electronic configuration would be something like 1s2, 2s2, 2p6, 10, and 3s2, 3p5. So 17 electrons are there in chlorine. However, there are exceptions, and particularly exceptions are the noble gases in period 1, 2, and 3. Period 1, 2, and 3, these noble gases, neon, argon, and krypton, they have this stable configuration. They appear to have larger atomic radii due to their closed electron shells. A closed shell means that a particular energy level or the shell is completely filled with electrons. For example, helium has full first shell, that is 2 electrons. Neon has full second shell, 8 electrons. So closed electron shells make atoms stable and less likely to form any bond or shrink through bonding. So when you measure their size in certain ways, they appear to be larger than expected, and for them we often consider van der Waals radii. So van der Waals radii is a quite overestimation of their radius, what their actual size is. So overall size decreases from as we go from left to right in a period, but there are some exceptions. Let's look at how atomic size changes as we move down a group in the periodic table. As we move down a group, the atomic size increases. Here take an example of lithium to cesium in group 1. You can see it steadily increases. So down the group, the atomic size increases. This happens for two reasons. Now new electron shells are added with each step down the group. Every new shell places the outermost electrons farther away from the nucleus, increasing the atomic radius. This is the first reason. Second reason is the shielding effect. Now what does a shielding effect means? Shielding effect means that the innermost electrons will shield the outermost electron from the nuclear forces. That means if outermost electrons are placed further away from the nucleus, the innermost electrons will give a shielding effect so that the outermost electron is loosely held. So it's kind of a repulsion. Inner electrons repel the outer electrons, reducing the effective nuclear attraction felt by them. This weaker pull allows the outermost electrons to spread out more, making the atoms larger. So here you can see in this diagram on the right that as we go down a column, say again from lithium to cesium, the circle representing the atomic size, it gets bigger. Now let's talk about exceptions. For example, this aluminium has larger atomic radius than gallium. There in this group where aluminium is supposed to be smaller than gallium, but it doesn't happen. So why does it happen? Because gallium is below aluminium in this group. It's supposed to be bigger, the atomic radius is supposed to be bigger, but it doesn't happen. So this is to contradict the trend. The reason lies in the presence of d electrons in the gallium. अगर हम लोग गैलियम का इलेक्ट्रॉनिक कॉन्फ़िगरेशन देखें तो ये पता चलेगा कि गैलियम हैज़ द इलेक्ट्रॉनिक कॉन्फ़िगरेशन ऑफ 3d10 4s2 4p1. Due to the presence of these 3d electrons, they do not shield the outer electrons effectively from the nucleus, and as a result the effective nuclear charge on the outer electrons is stronger, pulling them closer to the nucleus, and this makes gallium slightly smaller than the aluminium despite being in the row below. So while the general trend is an increase in atomic size down a group, D and F block elements can cause exceptions due to poor shielding by inner D or F electrons. Here I have summarized this for your ease. Across a period, atomic size decreases due to increasing nuclear charge, and down the group it increases because of more shells and greater shielding. So you can easily remember this trend with this mnemonic: across tight and down wide, across tight and down wide. Let's go through some questions, practice on atomic radius. Now I have added the answer. First is order of atomic radius, and the elements are sodium, magnesium, aluminum and silicon. So what will be the correct answer? Correct answer will be sodium. The atomic size of the sodium will be more than magnesium, which will be more than aluminum, and again which will be more than silicon. Why? Because all of these elements are in period 3, and as we move across a period from the left to right, we know that the atomic size decreases due to increasing nuclear charge pulling the electrons closer, right? So that is the first question. Next, arrange in increasing atomic radius nitrogen, oxygen and fluorine. So we know that these are in period 2 and atomic radius decreases across a period, so nitrogen is the largest and fluorine will be the smallest. So it will be fluorine, the smallest one, atomic size is less than oxygen and oxygen is less than nitrogen. So that is the order. Next question is arrange in decreasing atomic radius lithium, sodium, potassium and rubidium. So here here it is said that we have to arrange this in decreasing atomic radius. So these elements are in group 1, and as we go down a group, the atomic size increases because one electron shells are added and another is the shielding effect. So the correct answer would be rubidium is greater than potassium, which is greater than sodium, and again which is greater than lithium. So the next question is, which has the smallest atomic size? Sodium, aluminum, silicon or phosphorus? Now these are all in period 3, and as we go across a period, the size decreases from left to right, and phosphorus is the farthest to the right among these options: sodium, aluminum, silicon and phosphorus. So it has the smallest atomic radius, and the correct answer is option D, that is phosphorus. So next question is choose the correct order of atomic size. We are given 4 elements: beryllium, boron, carbon and nitrogen. So these all are in period 2, and we know that across a period the size decreases due to increasing nuclear charge. So the correct answer would be beryllium. The atomic size of beryllium will be more than boron, which in turn will be more than carbon, and atomic size of carbon is greater than nitrogen. So next question, compare the following: sodium atom versus sodium ion. This is an interesting question. Now sodium is in group 1 and period 3, present in group 1 period 3, but when it loses an electron, it becomes sodium ion. This is a cation. 3s1, if you remember it correctly, the last electron will be in the 3s orbital. So when it loses an electron, an entire electron shell will be gone, making the ion significantly smaller than the neutral atom or the parent atom. And when it loses an electron, the electron proton numbers are same, electron are lost, so the nuclear force will be more on the ion, and it will be smaller than the parent atom. So because of two reasons, the sodium ion will be smaller than its parent sodium atom, right? So that's all. Thank you all for joining this quick concept session on periodic trends. I hope this session helped you to understand the uh, key ideas clearly. If you have any questions, you can ask me in the comment section. I'll be taking up ionization energy in the next lecture. Keep learning and stay curious. Thank you again.